Hi everyone, today I'm going to be doing the worked example application questions from 4.7 of your Year 12 Jacplus textbook. So I think there's two of them and I haven't done these yet, so I'm looking forward. This first one, they say if P dollars is invested into an account that earns an interest at a rate of R for T years and the interest is compounded continuously, then A equals PE to the RT. So really, I mean, that's the important bit. There's far too many words in this question by the looks of it, where A is the accumulated dollars, so the amount that's going to be in the account after a certain amount of time. A deposit of $6,000 is invested at the Western Bank and $9,000 is invested at the Common Bank. Okay, so let's do two things, Western and Common. Obviously rip-offs of Westpac and Commonwealth. Anyhow, so at the same time, Western offers compound interest continually at a nominal rate of 6% per annum, whereas Common Bank offers common interest continuously at a nominal rate of 5% per annum. Okay, so we've got two different interest rates there, and we've got two different amounts. So let's write our equations. So the amount in the Western Bank is going to be, well, the amount that you invest, that's your P value, your principal, what you start with, times E to the power of R, which is the rate. So what's going to be the rate for Western? Western at 6%. So 6%, remember it's 6 divided by 100, so it's 0.06 T. So that's going to be our equation to represent the amount that's going to be in the account when you invest $6,000 in Western Bank. Now remember, we're investing a different amount in Common Bank, and that is $9,000. And our interest rate here is 5%, so it must be 0.05 T. So these are our two equations. So let's see, in how many years, correct to one decimal place, will the two investments be the same? Okay, so when they're the same, it must be that we're going to be equating them. So this is simultaneous equations. So we've got 6,000 e to the 0.06 t equals 9,000 e to the 0.05 t. Okay, so I'm going to divide this by 6,000 and this by 6,000, of course. What you do to one side, you do the other. So we're going to get e to the 0.06 t equals 9,000 over 6,000, so it's at 3 on 2. E to the 0.05 t. And then I'm going to divide each side by e to the 0.05 t. Now look, what's important with a question like this is that you have to know how much to do by hand. And essentially, because I mean, you could just put that into CAS here and solve it, but you won't get full marks. This might be 3 marks, and well, you would get 1 mark. So the idea is if you do it by hand until you get a exact value, and then you can convert it into a decimal. So if it was worth 1 mark, then we'll know we'd just do it straight on CAS. But if it's worth more than that, we definitely want to show some working out. Now we're dividing indices, so if we divide indices, we're going to subtract. So that's going to be e to the power of 0.01. T equals 3 on 2. So we're nearly there. We now just have to log both sides because we want to get rid of the exponential. So we end up with 0.01 t equals log e 3 on 2. And then now, well, I'm going to divide by, well, 0.01 is going to be 0.01. So divide 0.01. And of course, I'm going to get t equals 1 over 0.01 log e 3 on 2. And then, well, now you can just do it on CAS. So we get t, and this is going to be an approximate value, obviously, and that is, I'm just going to do that. Okay, so that's 40.5 years. And let's just check what the question actually asks. Correct to 1 decimal place. So there's no need to convert that 0.5 into 6 months. Remembering that we are looking in years, t is in years. So be careful in these that you know what unit you are dealing with. So 40.5 years. All right, let's move down. And this is something about population of foxes. So it's actually a really good, or I'd say tricky question in Cambridge about kangaroos, populations of kangaroos. So if you have a chance to do that, it might be a good idea too. Let's see, this one may well be the same or very similar. The population of foxes on the outskirts of a city is starting to increase. Okay, data collected suggests that the model for the number of foxes is given by this. Now what I would do straight away is draw that. So it may ask me to draw it, it may not, but I would draw it anyway, because if you draw the graph, you can get meaning from it. You can understand what it's doing. This is an exponential graph. It's obviously going to be flipped both ways there. And look, you can just draw that straight onto CAS. But also it is good to understand how we're getting the graph there. So this would be n of t against t. And I'd say, well, obviously if we start at 0 and go, I'd say, look, let's say 20 years. We might need more than that for the question, but I guess we'll find out as we go. It will have an asymptote. So this is y, it's equivalent to y equals negative 320 e to the negative 0.3t plus 480. So what we see is we're going to have an asymptote at y equals 480. And this is important because that tells us that, well, the population of foxes is never going to reach 480. It's always going to be below that. So I've just drawn that quickly on CAS, and what I'm getting is something like this. You may need to set your CAS so it goes, say, to -1. Sometimes CAS will not find the y-intercept, and it just means that it's not liking your 0. So so it's actually starting it at 0.00001. And even if that's the case, if it's so close to 0, if you haven't got the 0, it's not going to tell you your y-intercept. So if you can't get a y-intercept, just put it a little bit back, make your window go a little bit lower than 0, and you'll find your y-intercept. And that applies to any graph, not just exponential graph. So now that I have that, it's easy to analyze because the features of the graph represent different things. We can see at time equals 0, this y-intercept is the original number of foxes that are there. And as I predicted, it's going to ask us that first. So how many foxes were present initially at the start of the observation? So I'm going to do that with the algebra. So n of t, n of 0, equals 480 minus, oops, doesn't look like a 3, minus 320 e to the negative 0.30. Now anything to the power of 0 is 1, so that will go, and 480 minus 320 is 160. So initially we have 160 foxes. So look, you could also find that just on your graphs and tables. So it doesn't really tell us how they want us to do it because we've drawn the graph. I mean, if that's 1 mark, you can just get that from the graph. If it's worth more than 1 mark, then you'd want to show a bit more working out than that. Next, but in any case, look, n of 0. If it's initially, you should always write n of 0, substituting a 0 in. By how many had the population of foxes grown at the end of the first year? Now, this is a bit of a roundabout question because it's not saying how many foxes are there at the end of the first year. It's saying by how many has it grown. So we've got to find the difference between the original and after 1 year. So after 1 year, well, t must equal 1. So n of 1 is 480 minus 320 e to the negative 0.3 times 1. So let's see, I'm just going to cast that, and I am going to get 242.94 approximately. So I'm rounding that. And then, and it tells us, anyway, we've just we've subbed it in and we've rounded that. Now we can say by how many has it grown? So 242.94 minus 160, well, that's going to be, okay, so that is approximately 83. Okay, so just notice that this 0.94 is not a whole fox. So when you do your calculation, so you've got 242 minus 160, so that will give us 83. This is not a whole fox, but you know, we're not doing it exact, so it'll be approximately 83 foxes that we have more. What do they want next? After how many months does the model predict that the number of foxes would double its initial population? Okay, so that means n equals 320. So double the number of foxes. So we originally had 160. Now we're doubling that. We want to know when we're going to get to 320. So let's sub that in. So 480 minus 320 e to the neg 0.3t equals 320. And this is another one of those ones where you could solve it straight away on CAS, but if it's worth more than 1 mark, you really need to show how you're going to get that. You want to get to a stage where you have an exact value, and then you'll be able to convert it to a decimal. So 160, and then we've got divided by 320, so e to the neg 0.3t. So 320 minus 480 is negative 160, so that's going to be half here. So neg 160 divided by neg 320 is positive half. And then, well, neg 0.3t equals log e half. And then, well, we'll divide by negative 0.3, so t equals negative 1 over 0.3 log e half. And, well, now's the part where we can approximate it, and it's 2.31 there. Now, so the time is approximately 2.31. Now, let's go back and look at the units. So this is t is years. So we're looking t in years. So what this is telling us is we have 2 years plus 0.31 of a year. So this is not 2 years and 3 months. We have to say 0.31 times 12. And that gives us, let's convert it to a decimal, that gives us 3.72. So 2 years and 0.31 times 12 equals 3.72 months. So to find the number of months when you get a decimal of a year, you need to times it by 12, as we've done in other examples as well. So it's approximately 2 years and 4 months. So we'll round that up. So approximately 2 years and 4 months, and then the population will be doubled. All right, sketch. Oh, yeah, well, there we go. We already have sketched the graph. So here's the graph sketched here, showing all important features. And it doesn't give us a domain there, only that t is greater than 0. So I've done it to 20. I don't really need to put that 20 there. It was just when I was drawing it on CAS that I wanted to give a value that would be appropriate. Explain why this model does not predict the population of foxes will grow to 600. Okay, well, we kind of talked about that before. We've got an asymptote here at 420. So if we want to say that mathematically, so this is part D, part E, well, as t approaches infinity, so I should write as, excuse me, the number of foxes, or n of t, approaches 480. So we never reach 600. So you could explain that in a number of ways. I'm not sure how they do it in the book, but you could say there's an asymptote at y equals 480, so therefore the maximum number of foxes reached will never quite be 480. But I think this is most mathematical to do it like this. So as your t value approaches infinity, so the higher you go in time, well, your number of foxes would approach 480. So I believe that is it for the worked examples of applications.